Let's look at the effect of temperature on plants. Heat is a form of energy. There are other forms of energy, such as light energy, chemical energy, like in sugar. Heat is a form of energy, and temperature is the way we measure how much heat is in a body. Heat moves. It can be transferred from one body to another, causing a change in the temperature of both. For example, a cool lake can cool off the air around it. Heat moves in three different ways. Conduction is the flow of heat energy through a substance. Different substances can differ in the ability to transfer heat. Metal conducts heat relatively rapidly, air mostly slowly. Insulators are substances that conduct heat very slowly. In convection, transfer of heat is by a moving agent, by the agent moving itself. Heat may be transferred by a moving gas, such as steam or a liquid. When gas or liquid absorbs heat, its density changes, hot air rises, cold water sinks, and a circulation pattern can be created. Radiation, finally, is the transfer of energy without any connecting medium. Electromagnetic energy is an example. Energy from the sun is radiation energy. We generally measure temperature within a range of relevant to life on Earth using the Celsius or the Fahrenheit scales. But temperature in the universe has a much greater range of possibilities. Lord Kelvin, who was probably a guy with too much money and time on his hands, developed what he called the Kelvin scale to measure the range of heat energy throughout the whole universe. At absolute zero, 0 degrees Kelvin, molecular motion stops. At 10,000 degrees Kelvin, atoms no longer are intact, they come apart. This is thought to be the full range of temperature possibilities in the known universe. Life happens within a relatively narrow range from 273 to 373 degrees Kelvin on a scale of 0 to 10,000. Most of the rest of this lecture looks at temperature effects on plants, growth rate, photosynthesis and respiration, high temperature and cold injury, as well as chilling injury. Let's take a look. The effect of temperature on the growth rate of plants is largely through its effect on photosynthesis and respiration. These biological reactions will increase with increasing temperature up to a point. At certain high temperatures, the structure of biological molecules begin to break down. Growth rate increases to an optimum and then declines. So there's an optimum temperature range for any particular plant. The range will differ depending on the response and the species. Cool season crops, for example, have a different range than warm season crops. Let's take a look. Most cool season plants prefer a range of somewhere between 45 and 60 degrees Fahrenheit, whereas warm season plants prefer somewhere around 65 to 75 degrees Fahrenheit. As temperatures get much into the 70s for cool season plants, they'll actually grow slower than at the cooler temperatures. Here's some example of cool season plants, which prefer a temperature range of somewhere between 45 degrees and 60 degrees Fahrenheit. Might be a test question, by the way. In this range for cool season plants, photosynthesis is optimum. Below these temperatures, photosynthesis slows down. And above these temperatures, respiration increases more than photosynthesis, so the plant's burning more sugars than it's creating. Plants only grow when the accumulation of sugars through photosynthesis is faster than the burning of sugars through respiration. And the same is true for warm season plants, except they have a different preferred temperature range. Some prefer even a warmer temperature, such as truly tropical plants like banana. But in general, warm season plants grown in the northern hemisphere prefer 65 degrees Fahrenheit nights to 75 degrees Fahrenheit days. Warmer than that, respiration increases and the plants start to burn more sugars than they create. There are several ways of increasing temperature in the spring in the northern hemisphere. We use greenhouses, hot caps, and row covers. Here you can see some plastic row tunnels which are used to warm up the crops in the spring. These tunnels not only warm the plant up during the day, but prevent them from getting too cold at night. It's really important to get the cover off before it gets too hot underneath there. If it's left on too long, it could injure the plant and cause the flowers to fall off. There's my son Brian again. Remember him from the sweet corn picture? He's now a 40-year-old professor at the University of Rhode Island. The cucumber plants on the left were grown with a row cover, and the ones on the right were grown without a row cover. Cucumbers like it warm in the spring. This soil is red because I took this photograph in Australia, where some of the soils have a high iron content. But this temperature effect works in New England too. In Japan, row covers are used inside of unheated greenhouses to grow a high quality melon. These melons might sell for $100 a piece in the winter months. Again, both photosynthesis and respiration respond to increasing temperatures. As temperatures get too high, can be greater than photosynthesis. For good growth to occur, photosynthesis must be greater than respiration. And so there's a preferred temperature range in which this occurs. For cool season plants, again, someplace between 45 and 60 degrees Fahrenheit. For warm season plants, someplace between 65 and 75 degrees Fahrenheit. So you know there's a preferred temperature range for most plants. Let's now look at what happens when the temperature gets outside of this range. While the temperature range for warm season plants is somewhere between 65 and 75, they survive okay in the 80s. Once warm season plants get much above 95 degrees, however, things start to happen. Lots of water loss, proteins begin to denature, and you get accumulation of toxins. Above 1095 for too long, and warm season plants begin to fall apart. This will happen in some place in the low 80s for cool season plants. As temperatures get low enough, ice can form in the plant, damaging the cells. However, remember, freezing temperature of a plant will always be lower than 32 degrees Fahrenheit or 0 degrees Celsius, because 32 degrees Fahrenheit is the temperature where pure water freezes. Solutes, salts, things inside the cell lower the freezing point of the plant. For example, the ocean doesn't freeze at 32 degrees. It freezes much colder than that. Cells always have solutes in them, and those solutes lower the freezing point. The first area to freeze is usually between the cell walls, where the solute concentration is the lowest. As temperatures start to drop, some plants have the ability to transport water out of the cytoplasm through the cell membrane and deposit it in between the cell walls. Here, ice crystals can form without damaging the cell membrane. What this does, of course, is it concentrates the solutes, the sugars, and the salts inside the cell membrane, thus giving it an antifreeze effect. This concentrated solutes have a lower freezing temperature than pure water. There are three ways freezing can damage plants. The first is a cells can actually freeze to death. This happens at very low temperatures. More than likely, the greatest harm is from excessive water loss. Bright sun may increase leaf temperature above air temperature, allowing the plants to lose water through transpiration. This water is hard to replace because the ground is frozen, and as little replacement water can get to the roots. And of course, plants also can be damaged by frost heaving, which is caused by freezing and thawing of soil. This injures roots and exposes them to drying. Plants of tropical or subtropical origin are more likely subject to chilling industry, low temperature injury that occurs above the freezing point of the plant. Usually this involves temperatures between 35 degrees Fahrenheit and maybe 40 to 45 degrees Fahrenheit, but sometimes can occur at higher temperatures. It requires a period of continuous exposure to these temperatures for prolonged periods of time. The lower the temperature, the less time it takes for injury. Chilling rather than freezing injury happens at temperatures above the freezing temperature. Symptoms include brown or bleached areas in the leaves, kind of water soaked appearance, a loss of disease resistance. Sometimes flowers can fall off. These chilling injuries generally happen to warm season or tropical plants that experience cold temperatures. Different plants are more or less susceptible to cold temperature. Notice the beans here in the foreground are damaged by frost, but the spinach out in the back are doing just fine. One's a warm season plant and one's a cold season plant. Here you see some spinach plants that actually survived over the winter because there was a snow cover on them that kept them from freezing too much. The leaves were slightly injured. You can see the white areas, but they'll grow and thrive in the spring. So far, we've been looking at direct effects of temperature. Now we look at two indirect effects of temperature, hardening and vernalization. The term hardening refers to any treatment that results in a firmer or a harder plant tissue. Such treatment reduces growth rate, thickens the cuticle and the waxy layers around the leaf, and reduces the percentage of freezable water in the plant. Plant physically gets harder and can survive more cooler temperatures. Hardening results in an increased level of carbohydrates in the plant, permitting a more rapid root development than occurs in non-hardened plants. A, a pine tree, which can easily survive minus 32 degrees Fahrenheit during the winter time, may be killed by a rare 32-degree night in July because it's not been hardened. Here is some plants in a cold frame getting hardened off before they're ready to be put outside. Plants in this cold frame are protected from frost at night and kept warm during the day. On sunny days, the top would be cracked open to allow some air movement. Greenhouses used to grow transplants are also kept cool during the day by opening the vents slightly to prevent excessive heat buildup. The transplanting process can be a shock to a rapidly growing seedling, especially when it's set out into a cool, windy garden in the spring. This is especially true for transplants started in a greenhouse where it's nice and warm. These young seedlings can be made more resistant to cool temperature by hardening. A week before the plants are ready to set outside, they are watered a little bit less and kept a bit cooler. This hardens them and gets them ready to be put outside as a transplant and more likely to survive the shock. Vernalization is the second indirect effect of temperature we'll look at. This is the induction of the capability of flowering by a cold period, such as winter. For most species requiring vernalization, optimum temperatures are somewhere between 32 degrees and 40 degrees Fahrenheit. It takes a period from a couple of weeks to several months to induce flowering, depending on the species and the temperature. Biennials, for example, require cold temperatures before they'll flower. Carrots are a good example of a biennial that will flower after it's in the second year of growth. Carrots are shown here having gone to seed or bolted. The white seed heads of the carrots are very similar to Queen Anne's lace, which you may recognize as a common reed. This is because Queen Anne's lace and carrots are the same species. Of course, bolting is usually a bad thing for carrots, but in this case, this crop is being harvested for seed. Here you have a picture of two carrots. One in its vegetative state that produces a swollen carrot useful for consumption, and the other that's producing seed head. Carrots will grow for the first year, store up sugars in its root system, and the second year use those sugars to produce seed and a seed head. We'll now turn to some really practical ways of protection against frost, cold protection from cold. Site selection can help prevent frost damage. Plants grown at the bottom of the hill are more likely to be frosted than plants grown on a hill because cold air will drop down. Cold air is heavier and will actually drop down a slope. We've already seen how hot caps and row covers can help prevent frost damage by providing thermal insulation, such as this row cover here in this picture. On cold, very still nights, sometimes you can see a temperature inversion in which there's a layer of cold temperature around the plants, but just above it, a warm air layer sits. Big fans are used here in in the West, to grow pears, where the cold air and the warm air are mixed together to prevent frost damage. Humans, being inventive, have tried lots of things. Smudge pots full of oil or old tires were burned in orchards sometimes to create a bit of a cloud cover to try to prevent the plants from getting too cold at night. This didn't work and made a real mess and is totally illegal today. In the garden, people put electric gas burners out to try to keep plants warm. This doesn't work very well either. In the strawberry fields of South Florida, sometimes you'll see the irrigation system sprinkling water all night on a very cold night. The reason this works is because as water freezes, it releases heat and keeps the temperature of the plant above 32 degrees Fahrenheit. This can keep a strawberry crop protected on a very cold night. And the key is to keep irrigating the crop all night long until the sun comes up the next day and the frost disappears on its own. Here's a test question for you. An increase in the heat of an object is caused by what? Well, the increase in heat of an object is caused by an increase in molecular motion.